our silver iodide, define the thermal enthalpy of lattice formation. So that is going to be the enthalpy change when 1 mole of a solid ionic lattice is formed from its gaseous ions. So yeah, make sure you don't miss out, gaseous there, that's important. So some enthalpy data is shown in table 1. So here we've got a solid ionic compound, 2 aqueous ions. So that is going to be the enthalpy of solution. And here we've got gaseous ions, 2 aqueous ions, the same here. So those are going to be the enthalpy of hydration. So we need to use the data in table 1 to calculate the enthalpy of lattice of formation. So that is going to be gaseous ions to our solid ionic lattice of silver iodide. So let's quickly write that out now. So our silver, and we've got our iodide. Make sure you don't miss out these are ions, because that is the definition for enthalpy lattice formation, it's gaseous ions. Then we've got our solid ionic compound. Don't miss out the state symbols, guys. So yeah, and then what have we got here? So we've got the enthalpy of solution. So that is a solid ionic lattice to aqueous ions. So here we have our solid. So let's draw an arrow down. And we've got our aqueous ions. So we're going to have Ag plus aqueous, because this is our enthalpy of solution, and I minus. And that's also aqueous. And then here we see we've got gaseous ions, aqueous ions. So that is going to be the enthalpy of hydration. So draw another arrow. Try not to do it how I've done it, so the arrows are crossing over. You guys can do it a lot better than me, I'm on an iPad. But yeah, so, and then we've got to write in what we've got here. So enthalpy of solution here is plus 112. Here, the enthalpy of hydration for silver is minus 464. And then here for iodide it is minus 293. Okay, and then this is our unknown, so this is X. So what I like to do now is check that it's all 1 mole, because, the definition, as we saw here, it's all 1 mole. So yeah, as we can see, it's all 1 mole. So yeah, and then we're going to write an equation. So X here. So if we're going from here, from here to here, Hess's law tells us that no matter what route we take, as long as we start at the reactants and end at the products, it's going to be the same enthalpy change. So even though we don't know what this enthalpy change is, because we're going from here, the reactants, to the products, but we're taking this alternative route this way, it's still going to be the same enthalpy change. So we can say the enthalpy change, X, is going to equal minus 464, minus 293, and then here we see the arrow is going the wrong way, so we are going to minus 112. So if we put that in our calculator quickly, minus 869, and make sure you don't miss that minus, because that means the reaction is exothermic. A calculation of the enthalpy of lattice formation of silver iodide based on a perfect ionic model gives a smaller numerical value than the value calculated in 1.2. So 1.2, this is like our actual data, this is what actually happened, and that's our enthalpy change minus 869. And if we're looking at the perfect ionic model, we have a smaller numerical value, so it's less exothermic, less energy given off. So the perfect ionic model looks a bit like this. You have your ions, and they're kind of arranged pretty perfectly like that. There's not really any polarization. Whereas when we have covalent character, what happens is this, this cation here, the metal ion, it is very polarizing. It has a high charge density. For example, this happens with silver, as we see. Silver tends to be quite polarizing. So what happens is it kind of distorts the electron cloud. So if you imagine like the electrons are somewhere in there, they're getting pulled closer to the cation because it's very polarizing and charge dense. So it's pulling the electrons closer. And basically what this means is that the bonds are stronger. So what we say is silver iodide has covalent character. Therefore, stronger forces of attraction. Identify a region that could be used to indicate the presence of iodide ions. Halide, iodide, test for halides, silver nitrate. So that is going to be AgNO3, your silver nitrate, and we're going to form a yellow precipitate. Write it out for the exam, I'm lazy, but yeah, write precipitate. This question is about acidic solutions. The acid dissociation constant K for ethanoic acid is given by the expression. The value of K for ethanoic acid is 1.74 times 10 to the negative 5 moles per decimeter cubed at 25 degrees. A buffer solution with a pH of 3.87 was prepared using ethanoic acid and sodium ethanoate. In the buffer solution, the concentration of ethanoate ions was 0.136 moles per decimeter cubed. Calculate the concentration of ethanoic acid in the buffer solution and 3 significant figures. Oops. So first thing I always recommend you doing in these acid-based questions is rearranging for what we want. So we want to find the concentration of ethanoic acid, which is there. So if we quickly rearrange that, So that is the rearranged version for our ethanoic acid concentration. So next we want to just put in all the values that we have. So we see we've been given the pH of 3.87, and therefore we can find the H+. So if we do H+ equals 10 to the negative 3.87, we'll get our answer, which is 1.3489 times 10 to the negative 4. So that's our concentration of H+. And then what else does the question give us? It's got our concentration of ethanoate ions, which is that, and we are given the Ka. So let's just put it into the equation. So ethanoate ions is 0.136. Concentration of H+ is 1.3489 times 10 to the negative 4, and that is all over our K, which is 1.74 times 10 to the negative 5. So if you put that in your calculator, you'll get the answer, which is 1.05. There you go. In a different buffer solution, the concentration of ethanoic acid was 0.260 mole decimeter cubed, and the concentration of ethanoate ions was 0.121 moles per decimeter cubed. And then we're adding a 7 times 10 to the negative 3 mole sample of sodium hydroxide to 500 centimeter cubed of this buffer solution. Calculate the pH of the buffer solution after the sodium hydroxide was added. Give your answer to 2 decimal place. So we need to look at what is actually being added to what. So we have our acidic buffer of ethanoic acid, and we are adding sodium hydroxide to it. So we have our ethanoic acid, and we are adding sodium hydroxide. This is going to make our salt. You could write it out in full, but I'm lazy, so I'm just going to write A-. And also water, salt plus water. So it says we want to calculate the pH after it's been added. So first we need to look at what we originally have. So we want to write our initial moles, our change, our equilibrium, and lastly our concentration, because that is what we have in the Ka equation. We use concentration, square bracket. So our initial moles of ethanoic acid, so it says we have 0.260 moles per decimeter cubed, that's concentration. So we want to find moles, so that's going to be 0.260 times our volume, which is 500, but we need that in decimeter cubed, so we're going to divide it by 1,000. That will give us our moles of ethanoic acid, which is 0.130. And our moles of sodium hydroxide that we are adding is 7 times 10 to the negative 3. And it says our concentration of ethanoate ions was 0.121, so that is going to be 0.121 times 500 over 1,000. That'll give us our moles, which is 0.0605, and we don't really care about water. So we need to look at what we're going to have in the equilibrium over here. So to look at that, we need to see what is limiting. This is a lot smaller than this, so therefore this is going to go to 0 at equilibrium because it's limiting. We don't have much of it. So this is going down by 7.00 times 10 to the negative 3 because it's going to 0. If this is going down by this much, so is this. So this is going to go down by 7 times 10 to the negative 3. And that's going to give us our equilibrium moles of ethanoic acid after adding, and that is going to be 0.123. There we go. So now we need to find our moles of our A- or our salt or our ethanoate ions. So if this, so if we've gone down by this much, we're going to go up by the same amount because it's 1 to 1, as we see here. So this is going to go up by 7 times 10 to the negative 3. So that will give us our equilibrium moles of ethanoate ions is going to be 0.0675. There we go. So now we want to turn this into our concentration values because that is what is in our Ka equation. So it doesn't give us the new volume, it just says it tells us the original, but it doesn't give us the new. So what I'm going to do is I'm going to write a kind of expression for this. I'm just going to say it's over volume. We don't really care about this because we have none of this, but yeah, and over volume. So there we go, and we want to put this into the Ka equation. The question has told us earlier, this is our value for Ka, 1.74 times 10 to the negative 5. So first let's just write out our Ka equation, so our products. So we're going to have H+, our A-, all over our HA. And we want to find H+, so we want to rearrange for that. So that is going to be Ka multiplied by our HA concentration divided by A minus concentration, and that will give us our concentration of H plus. Now we just want to put in our values. So yeah, we know the K. So we know our Ka value for ethanoic acid, same acid, is 1.74 times 10 to the negative 5. And we already have the concentration for HA and A minus. So is our Ka, and that is going to be multiplied by our HA, which we worked out to be 0.23 over volume, divided by our A minus, which we calculated to be 0.0675 over volume. And this will give us our H plus concentration. And as we can see here, the volumes cancel out, so we can just use our moles. And if we put that into the equation, we'll get our concentration of H plus. And what you do is you just put that answer into negative log 10 H plus, and that will give you your pH. And your answer should be 4.50, always the 2 decimal places when you're using working out pH. Calculate the pH of a 0.0131 mole per decimeter cubed of calcium hydroxide at 10 degrees. Give your answer to 2 decimal places. So first, for this question, I think it's important, just so you don't make any silly mistakes, to write this out as an equation. So calcium is in group 2, so therefore our calcium hydroxide is going to look like this. We're going to have 2 of them, 2 hydroxides, because this calcium forms 2 plus. We need 2 of these to balance that. So this is a strong base, so we want to see what at equilibrium it's going to fully dissociate. So we're going to have calcium 2 plus, and we're going to have 2 OH minus. Now, what equation involves OH minus? Kw. So if we write out our Kw equation, so the question tells us that we have 0.0131 mole per decimeter cubed of calcium hydroxide, but we see here there's 2 of those for every one of these, so our concentration of OH minus is going to be double this. So we're going to write out, first of all, actually I recommend rearranging this first to find H plus, because we're trying to find the pH. So that's going to be Kw divided by OH minus equals H plus concentration. So we know the Kw from earlier. We've already been told for water at this temperature at 10 degrees is this. So 2.93 times 10 to the negative 15. Our OH minus concentration is going to be 2 times our 0.0131, and if we divide those together, we will get our H plus concentration, and that will give you 1.118 times 10 to the negative 13, and that is our H plus. So if we want to find the pH, we just do negative log 10 to 1.118 times 10 to the negative 13. That will give you your pH, which will equal 12.95. 2 decimal places. 0.0131 mole decimeter cubed calcium hydroxide solution at 10 degrees was a saturated solution. A student added 0.0131 mole of magnesium hydroxide to 1 decimeter cubed of water at 10 degrees and stirred the mixture until no more solid dissolved. Predict whether the pH of magnesium hydroxide solution formed at 10 degrees is larger than, smaller than, or the same as the pH of calcium hydroxide solution at 10 degrees, and explain your answer. So we have the same quantities, the same concentrations. This is moles, but we have 1 decimeter cubed, so the concentration is the same. So we just need to look at this as in what is changing. And the way to look at this is in terms of solubility. So if you remember, hydroxides in group 2, as you go down the group, they become more soluble. If you remember, sulfates, they get less soluble because barium sulfate is insoluble. So it's just the opposite. They become more soluble as you go down the group. And magnesium is above calcium. So therefore, magnesium is less soluble. So magnesium hydroxide, if it's less soluble, less of this is going to dissociate into OH minus, which is alkaline. So therefore, it's going to be less alkaline or more acidic or have a lower pH. so it has a lower pH, and that is because it is sparingly soluble. A sample of titanium was ionized by electron impact in a time-of-flight mass spectrometer. Information from the mass spectrum about the isotopes of titanium in the sample shown in Table 2. We've got our MZ values for the different isotopes and their relative abundance. Calculate the relative atomic mass of titanium in this sample. Give your answer to one decimal place. So this is kind of just the equation that you need to memorize, and it's the MZ multiplied by the abundance divided by 100, because this is a percentage. If it was not the percentage, it was just the total, then you divide it by whatever the total is. But we're working with percentages here, so it's going to be divided by 100. So yeah, so it's just going to be 46, the MZ, times the abundance, which is 9.1, plus 47 times 7.8 plus 48 times 74.6 plus 49 times 8.5, and that is all going to be divided by 100. And if you put that into your calculator, you'll get your answer as 47.8. And to avoid not messing up, I recommend collecting all these terms and writing it out as, and then just dividing that by 100, because it can get a bit messy and you're more prone to error. I recommend just putting these in your calculator first, calculating what it is, and then dividing by 100, just to avoid any silly mistakes. Write an equation including state symbols to show how an atom of titanium is ionized by electron impact, and give the MZ value of the ion that would reach the detector first. So it's important to note that it says how an atom of titanium is ionized. So we're not already dealing with an ion, we're dealing with an atom and we're turning it into an ion. So this is the first ionization energy, and it's electron impact. So we're going to add our titanium and make sure it's gaseous. It's always gaseous in these equations for ionization. And we are adding an electron because we're firing a high energy electron at it. And we are going to produce our titanium ion because we've knocked off an electron, and we have 2 electrons here. There you go. And the MZ value is just going to be whichever one has the lowest mass, because that is going to have the fastest travel time in the mass spec, and that's going to be 46. So it's therefore going to reach the detector first. Calculate the mass in kilograms of one atom of 49 titanium. So for this question, we know our titanium has a relative mass of 49. So if the mass of titanium is 49, but we want to find what one atom is, we're going to divide that by Avogadro's constant. If that's not it, it's asking for it in kilograms. So whatever that answer is, we're going to divide that by 1,000 also, because if you remember, this here is in grams per mole. So to get that into kilograms per mole, we divide it by 1,000, and that'll give you your answer, which is 8.137 times 10 to the negative 26. There you go. In a time-of-flight mass spectrometer, the time-of-flight T of an ion is shown by the equation T equals D square root m divided by 2e. In this equation, D is the length of the flight tube, m is the mass in kilograms of an ion, and E is the kinetic energy of the ions. In the spectrometer, the kinetic energy of an ion in the flight tube is 1.013 times 10 to the negative 13 joules. The time of flight of a 49 Ti plus ion is 9.816 times 10 to the negative 7 seconds. Calculate the time of flight of the 47 Ti plus ion and give it to appropriate significant figures. So, there are multiple different ways for going around this question. For me, the one that is most systematic and makes the most sense is using all the data given for the 49 Ti plus ion, and if we rearrange it to find the distance, that's the only thing that's not provided in the question. So if we rearrange to find the distance using the data given for the 49 Ti plus ion, we can use that distance to plug it into the equation and find the time of flight for the 47 ion, which is what we want to calculate. So our 2 equations, we've got the one that's given, and we need to rearrange this also for distance. So that is going to look like so these are our 2 equations that we're going to be using. So first we're going to use this one first, and we're going to use this one second. And we want to find the distance first. So we need to look at what the question gives us. It gives us the time of flight for the 49 ion. So that's 9.816 times 10 to the negative 7. divided by the square root of the mass, which needs to be in kilograms, and we're using the 49 one right now, because that's all we have. So if this is in grams per mole, we need to turn that into kilograms. So that's going to be 49 times 10 to the negative 3, and we're going to divide that by the kinetic energy times 2, because there's 2 in the equation. So that is going to be 2 times the kinetic energy, which is given there, 1.013. So if you put that into your calculator, you'll get your answer for the distance to be 1.99 times 10 to the negative 12. And now, if we use this new calculated distance and put it into this equation here, but with the 47 mass instead, because that's the only thing that's changing, we can find the time of flight for the 47. So if we do our distance, 1.99 times 10 to negative 12, put that in brackets, and we're timesing that by this here, multiplied by the square root of the mass, which is now 47, but we need it in kilograms, so times 10 to the negative 3, and that is again divided by 2 times the kinetic energy, which is there. Can't be asked to write it all out, but you guys write it out in full in your exam. So if you put that all into your calculator, you will then get your time, which is 9.584 times 10 to the negative 7. However, don't forget, we need this to the appropriate number of significant figures, so that is going to be 9.6 times 10 to the negative 7. There you go. Titanium chloride can be made from titanium oxide as shown in the equation. Some entropy data is shown in table 3, and we've also got our enthalpy change here. So here is the entropy in joules per Kelvin per mole. Use the equation and the data in table 3 to calculate the Gibbs free energy change for this reaction at 989 Celsius. Give your answer to appropriate number of significant figures and explain if the reaction is feasible. So, first of all, let's write out the equation that we're going to be using, which is delta G equals delta H minus T delta S. And I'd like to put this in brackets. So, let's look at what we've got. So we've got delta H, and what else have we got? So we've been given all this entropy data, so we're going to need to use that to calculate delta S. But first, what is our T? Our T is 989 Celsius, so we need to convert that to Kelvin. So if you do 989 plus 273, that's going to give you your temperature in Kelvin, which is 1262. Now we need to find our entropy change, delta S. And so that's going to be our products minus our reactants. Any change in reaction is going to be the end minus the start. So I like to quickly annotate this table here just to make it a little bit easier, just to avoid any silly mistakes. So our products are on the right and our reactants are on the left. And I like to quickly add all the molar ratios. So we've got 2 there, got 2 there, and we've got 2 there. So then we just need to work out the start minus the end of this. So if we make this into a little equation, we're going to have 2198 so that's our products done. Now we need to minus that from our reactants. So we've got 50.2 plus so there you are. And if you collect all the terms, you will get 649 and 507.6. So if you just do that there, you'll get your entropy change to be 141.4 joules per Kelvin per mole. But if we see there is an issue here, this is in joules, whereas our entropy change here, enthalpy change, here is in kilojoules. So we need to do something about that. We're going to need to convert that. So if we put this all into our equation to calculate our delta G, we've got our enthalpy change, which is minus 60. And then that is going to be minus our temperature, 1262 times our entropy change, but we're going to need that in kilojoules, so we're going to times that by 10 to the negative 3, because that will be dividing it by 1,000, and we are therefore putting it into kilojoules. So if you put this into your calculator, you'll get your answer to be minus 238, and that is your delta G. Then it says use your answer to explain whether the reaction is feasible. So if delta G is less than or equal to 0, the reaction is feasible. So we've got minus 238, that is a negative, so therefore the reaction is feasible. So we say delta G is less than 0, so the reaction is feasible. Or you can say spontaneous. This question is about some period 3 elements and their oxides. Write an equation for the reaction of phosphorus with an excess of oxygen. So you can either write it as just pure phosphorus, or what I do is P4, and we're adding it with an excess of oxygen. So let's add the oxygen, and unfortunately this is just the one that you need to remember, and you form P4O10. That is the oxide of phosphorus that you need to remember from the topic period 3 and their oxides. So we just need to balance this quickly. Phosphoruses are already balanced, as we see here, and we've got 10 oxygens here, 2 here. So to balance this, we just add a 5, and there you go. Describe a test you could carry out in a test tube to distinguish between sodium oxide and the product of reaction 6.1. So our product of 6.1 is P4O10, and we need to distinguish this with sodium oxide. So immediately I'm thinking we can add water to this, and if we add water to our phosphorus oxide, we're going to produce phosphoric acid. And if we add water to our sodium oxide, we're going to produce sodium hydroxide. One is an acid and one is a base. So if we add water, and then we also use pH probe to measure pH. You should always say what you're doing when measuring pH. So we're using a pH probe, to measure the pH, and the fundamental difference is that one is an acid, one is a base. So our sodium oxide with water solution pH will measure 12 to 14, whereas our phosphorus oxide pH will measure 1 to 2. So there you go, that's the difference. State the type of crystal structure shown in silicon dioxide and in sulfur trioxide. So silicon, if you remember, is in group 4, and therefore it's kind of similar to carbon. It can form this macromolecular giant structure. So it's macromolecular. You can call it macromolecular, or you can also call it giant covalent. And our sulfur trioxide, that is just a simple molecule, or it's molecular. So there you go. Explain why silicon dioxide has a higher melting point than sulfur trioxide. So, as we've seen before, this is macromolecular, our silicon dioxide, whereas our sulfur trioxide is just simple molecular. So, if we're melting, we're going to be breaking the forces in between our atoms or our ions. So, in this case, in silicon dioxide, we're going to be breaking covalent bonds, as it's macromolecular, as the bond in between atoms in silicon dioxide is a covalent bond, and that is very strong and requires a lot of energy to be overcome. Whereas our sulfur trioxide, this is a simple molecule, so the only force in between it is going to be van der Waals forces. You could also say dipole-dipole forces, because there is permanent dipole, but you could just say intermolecular forces. So what requires more energy to be overcome? The covalent bond, whereas our intermolecular forces takes less energy. So we just need to put that into writing. So covalent bonds between atoms in our silicon dioxide, whereas intermolecular forces, write it out full in your exam, between atoms in sulfur trioxide. So intermolecular forces are much weaker than covalent bonds. So covalent bonds require much more energy to be broken and our van der Waals, or our intermolecular forces, or our permanent dipoles, require less energy to be overcome. There you go. Also, write it down in full here. I didn't say to be overcome, but you need to write it out: to be broken or to be overcome. Write an equation for the reaction of sulfur trioxide with potassium hydroxide solution. So you kind of just need to remember that these covalent oxides are indeed acidic, and we're reacting it with a base. So this is just going to be an acid-base reaction. So let's just write out what we know. We know we got sulfur trioxide, and we're reacting it with potassium hydroxide. So that's our KOH. And because this is an acid-base reaction, we're just going to form a salt and water. So our salt, you kind of just need to think, what can we make? So I'm seeing SO3, I'm thinking of a sulfate ion, SO4, 2-, and we've got K here, so we can make K+. So we could make K2SO4. Remember, this is 2-, so this needs to be 2+. So, and we're also going to make water. This isn't balanced though, so to balance this, we just need to look 2 there, so we're going to add 2 there, 2 potassium for 2 there, and there you go, that is all balanced. Write an equation for the reaction of an excess of magnesium oxide with phosphoric acid. So, a little useful memory trick that I used to use is if we've got ionic, if we've got an oxide, and it's ionic, it's going to be alkali, whereas if we have a covalent oxide, it's going to be acidic, or act as an acid in water. So if we've got magnesium oxide, that is ionic, so therefore that is alkali, and we're reacting it with an acid. So if we're reacting these two, we can therefore derive this is an acid-base reaction, and we're going to form a salt and a water. So if we've got our magnesium oxide and we're reacting with our phosphoric acid, if you remember that is H3PO4, we're going to form a salt and water. So we see we've got the phosphate ion here, and we've got our magnesium here. So we can form magnesium phosphate. However, this isn't balanced because we remember, this is 3- because 3 hydrogen here. So therefore 3-, 3+, hypothetically. So we need to balance this. If magnesium is in group 2, that forms 2+, and this is 3-, we can make them both +6 and -6. So if we put 3 there, put this in brackets, put 2 there, there is our salt. And we also are going to make water, because we're making a salt and water. And we just need to balance this now. So if you see we've got 3 magnesiums here, we're going to need 3 here. And if we next balance the hydrogens, we see 2 there, 3 there. So if we put a big 3 there and a big 2 there, we are balancing the hydrogens, making them both 6. And that also simultaneously balances the oxygens. So there you go, there is your balanced equation. Draw the displayed formula of the undissociated acid formed when sulfur dioxide reacts with water. Just get rid of this. So if we're reacting sulfur dioxide with water, you should be able to derive that we are going to form H2SO3. Because if it was sulfur trioxide, we'd form H2SO4. But we're working with sulfur dioxide here. So you should be able to, you kind of need to just remember this. But, if what I do is I remember sulfuric acid, the structure, you kind of just memorize that this is what it looks like. However, this is sulfur dioxide, so we're going to form H2SO3, not H2SO4. So we can just get rid of one of these here, put a lone pair there, and there you go. There is your undissociated acid. Undissociated meaning that we haven't lost an H+ yet, or either the H+, because this is a diprotic acid. So there you go. Solution A contains the compound. State the type of bonding between oxygen and hydrogen in this compound. So the bonding between oxygen and hydrogen is right here, and that is in the ligand, not the coordinate bond, that's in the ligand, so therefore it's just a covalent bond. State why the chloride ions in this compound are not considered to be ligands. So we see here, they're not donating any electrons to the central copper transition metal. They're not acting as ligands, they're not in this, they're not in these circle brackets in the complex, they're outside of the complex. So we could say that Cl is not donating lone pair to copper 2+. And just to point out, we know that it's copper 2+ here because we need 2 Cls to balance out the 2+ charge, because these are group 7, they form -1 ions, so we need 2 of them, so that is 2-, this is 2+. An excess of ammonia was added to a sample of solution A to form solution B. Write an ionic equation for the reaction that occurs when solution A is converted into solution B, and state the colour of solution B. So our solution A is this here. It's our copper 2 plus hexa aqua coordinated, and we're adding an excess of ammonia. So we need to write an ionic equation. So this is the one that you need to remember for ligand substitution. It's the only one you get ligand substitution is when you're adding excess ammonia, not dilute. We're adding excess ammonia to copper 2 plus is the only example where you get ligand substitution. So let's write out what we know. We've got our copper hexa aqua complex. That is solution A. And we are adding ammonia in excess. And what happens is 4 of the 6 ligands are substituted by ammonia. So if you write this out here, and then the 2 H2O ligands, and it is a 2 plus complex, and also the 4 H2O ligands that are being kicked off from the original 6 hexa aqua complex. And the colour, when we get this ligand substitution, we form a dark blue solution. Aqueous sodium carbonate was added to another sample of solution A to form a blue-green solid C. Identify the blue-green solid C. So we've already identified here that because of this is 2 plus. So if we're adding a carbonate to a 2 plus, we're going to form copper carbonate. Because we have a 2 plus, we form carbonates. If we have 3 plus, remember the complex is acidic, it acts as an acid. And if we add acid to a carbonate, that's the one where we get salt, water, and effervescence, so CO2. Reagent D was added to another sample of solution A to form a yellow-green solution. Identify reagent D and write an ionic equation for the reaction that occurs when the yellow-green solution is formed from solution A. And so we need to identify it and write an equation. So we have our solution A, which is a hexa aqua complex of copper, and we know the copper is 2 plus due to this ionic bond here, 2 minus 2 plus. So this is unfortunately one of the ones you just need to remember, but you can kind of work it out. If we're forming a solution, we know the complex we're forming is going to have a charge, because anything in this topic, if it has a charge, it's a solution. If it's got no charge, it's neutral, it forms a solid precipitate. So we're forming a solution, and we know it's yellow-green. So it's gone from our blue solution to a yellow-green solution. So we need to think what is going on here. And this is unfortunately just one of the ones that you need to remember, but we are swapping all of the 6 water ligands for chloride ligands. And this is unfortunately, just one of the ones that you need to remember, that chloride ligands are a lot bigger than these water ligands, so we can only fit 4 of them around copper, 4 coordinate bonds of these chloride ligands around copper. So so if we start with the equation, we have our copper hexa aqua complex, and we are adding our chloride ligands, and we're forming our copper chloride, and there is 4 of those chloride ligands. And if we look at the charge, we know this is 2 plus, and if we're adding 4 of minus 1 chloride ligands, this is going to be 2 minus overall, because we've got 4, that's 2 minus overall. And we are also going to be displacing all 6 water ligands, so we form 6 H2O. And if we're adding 4 chloride ligands here, we're going to need 4 here. And if we identify the reagents, we can't just add a negative anion, we can't just add an ion, you need to add it as a compound. So where can we add chloride? HCl. Strong acid fully dissociates into chloride ions. Explain why colorimetry cannot be used to determine the concentration of solutions containing CuCl2-. In your answer, refer to the electron configuration of the metal ion. So, to measure the colour of something, colorimetry, measuring the colour, we need to have a transition metal, because transition metals are coloured. And if the definition of a transition metal is something that forms a stable transition metal ion with an incomplete d subshell, we need to use that definition to determine whether or not this can be measured, if it has a colour or not. So, to see if this has a colour, let's look at the oxidation state. So this is going to be 2 minus, and it has a minus 1 overall, so this is going to be plus 1. So the copper is in the plus 1 oxidation state. So if we look at copper, usually, its electron configuration usually is 4s1, 3d10. And it does this because if you look at based off the periodic table, it should be 4s2, 3d9, but it's one of those weird exceptions where you lose an electron from the s subshell to completely fill the d subshell to have 10 electrons, because it's more stable if it's either half or completely filled. So 10 electrons, more stable, you lose an electron from the s subshell. So this is copper's usual electron configuration. It's usually 4s1, 3d10. But in this scenario, it's in its plus 1 oxidation state. If it's plus 1, it's lost an electron. So it's lost an electron from the 4s orbital. So the electron configuration of copper in the +1 oxidation state is 3d10. And back to our definition, we said a transition metal, it should form a stable ion and have an incomplete d subshell. That's a stable ion, but this is not an incomplete d subshell. So if we've got a complete d subshell, the d electrons can't be like split to the different energy levels. You can't have that light that is going to be absorbed and some is transmitted and then that gives you the color. That doesn't happen because we have a complete d subshell. So what you say is 3d10 / complete d subshell. So copper has that 3d10 complete d subshell in its +1 oxidation state. So if you can't have this light being absorbed into the split d subshell, if we can't split the d subshell, it's colorless. So if something is colorless, we can't measure its color by colorimetry. It has no color, it's colorless. So there you are. A lot of explaining, but yeah, 2 marks. This question is about ion testing. Describe how the student could distinguish between aqueous solutions of potassium nitrate and potassium sulfate using one simple test tube reaction. So if we look at our potassium nitrate, you got your nitrate here, that is NO3 minus, and we've got our sulfate, K2SO4, so that is going to be SO4 2 minus. So straight away, sulfate, test for sulfates is you add barium. You can either add this as barium chloride, you can add barium hydroxide. You can't just say add barium 2+. You can't do that. You have to add it with something. So BaCl2, or you could add barium hydroxide. Just do one or the other, don't write both. But yeah, so with nitrates, there will be no visible change. No change. Whereas with sulfates, you get your barium sulfate, which if you remember group 2 is insoluble, so you get your white precipitate of barium sulfate. Describe how a student could distinguish between aqueous solutions of magnesium chloride, MgCl2, and aluminium chloride, AlCl3, using one simple test tube reaction. So, if you remember, group 2 hydroxides make a white precipitate, which changes in solubility down the group, so it can redissolve down the group. Whereas aluminium, that will also form a white precipitate. So you're thinking, what can we do here? So this question is quite devious, and like lots of people are going to get this wrong, or just like not think of it. But, so yeah, what happens is, if you had excess sodium hydroxide is, of course, the source of OH minus, as is a strong base, fully dissociates. So if we add our OH minus here, with our MgCl2, we're going to get a white precipitate of magnesium hydroxide. So that's our white precipitate of magnesium hydroxide. And here, we also get a white precipitate of aluminium hydroxide. But what's devious about this is if you add excess sodium hydroxide, it will redissolve. And my understanding of this is because it's aqueous here. When we add hydroxide, at first, we're going to get this. We're going to get our this insoluble white precipitate of aluminium. And what happens is because aluminium is amphoteric, it can act as an acid or a base. So if we add excess base, this is going to act as an acid, and we're ultimately going to form, you can form that, and obviously it can keep on going. I haven't written the water ligands, but yeah, it can keep on going, and essentially this will redissolve because it has a charge. It's no longer a solid precipitate. We've added excess base, so it's gone to this. It's now charged. It's going to redissolve. So what we can say is white precipitate that redissolves in excess sodium hydroxide. There are several stages in the industrial production of methanol from methane. The first stage involves a gaseous equilibrium between the reactants methane and steam and some gaseous products. Figures 1 and 2 show the percentage conversion of methane into the gaseous products under different conditions at equilibrium. So here we've got the percentage conversion of methane at a constant pressure, but we're changing the temperature. And as we can see, as temperature increases, our percentage conversion, or our yield, increases, but then it plateaus here at about 80 degrees Celsius. And then here we see the percentage conversion of methane to our methanol, again, and the gaseous products, and we see that it decreases over time as pressure increases. So as our pressure increases, our yield decreases. So, to deduce the optimum conditions for the industrial conversion of methane and steam into the gaseous products, explain your deductions. So let's first just look at what we've got on the graph, and here we see that yield, here, our percentage conversion increases as temperature increases. So let's just say that. write it out in full. But yeah, yield increases as temp increases. However, after a certain temperature at 880, there is no further conversion of methane into the gaseous products. Of methane into gaseous products. And then if we look at our other graph here, we see that our yield decreases as our pressure increases. As pressure increases. So our yield decreases as our pressure increases here. So there we go. And then next we need to kind of deduce the optimum conditions for what we would personally do if we were to convert our methane into our methanol and our gaseous products. So I would say our optimal temperature is around here at 880, because if we were to go for 900, we don't get any more conversion. It's still the same here, approximately. It's like the same percentage conversion, but at a higher temperature, that's going to be more expensive. So optimal temp is going to be 880 degrees for maximum yield. And now we need to explain why wouldn't we do 900, and that is because no further conversion into gaseous products at 900 degrees and more expensive for higher temperatures. Because if you imagine, you're working in industry and you're trying to make these high temperatures, that's going to be more expensive. You're going to need to use more resources. So yeah, so optimal temperature is around 880, as we've said. Now we need to decide on what is going to be the optimal pressure. And we see we have the highest conversion, we have the best yield at the lowest pressure. But if we use a pressure that's too low, we're just not going to get any, the rate is just going to be so slow. Like if you imagine if you have a very small pressure, you have a very large container, our two molecules are just not going to collide. Like it's going to take ages to convert it. Even though we have this high conversion here, it's going to take ages for them to collide. The rate is going to be very, very slow. So we can say that low pressure will be too slow / slow rate. So I'd say probably a compromise. We don't want to use this low pressure because there's not going to be many collisions, even though we have this high conversion. Because this is an equilibrium. So I would say we want to compromise and use a pressure somewhere in the middle. So between here and here, probably, I would say more about here, around 2000 kPa. So compromise with 2000 kPa pressure. Because at this pressure, we've got a decent pressure, so our particles can collide, and we've still got a pretty good conversion at around 60, probably around 70%. So yeah, that's not too bad, and that should be it. The equation shows the final stage in the production of methanol. So we've got our carbon monoxide gas, our hydrogen gas, and our methanol. And I think it's important to just kind of highlight the fact that this is a 1:2:1 ratio because of our molar coefficients, our stoichiometry. So 20.1 moles of carbon monoxide and 24.2 moles of hydrogen were placed in a sealed container. An equilibrium was established at 600 Kelvin. The equilibrium mixture contained 2.16 moles of methanol. Calculate the amount in moles of carbon monoxide and of hydrogen in the equilibrium mixture. So I'm going to just write it out like this here because I can't be asked to write it out again, but you guys can if you want to. So I kind of like to use these two lines here to represent the equation, the equilibrium thingy. So the question tells us we've got 20.1 moles of carbon monoxide and we've got 24.2 moles of hydrogen, and this is just as they were placed in the sealed container. No reaction has yet happened, so we have 0 moles of methanol. So this is our initial, and then we should write our change and our equilibrium. So it says we've got 2.16 moles of methanol at equilibrium. So 2.16 moles of ethanol at equilibrium. So this has gone from 0 to 2.16. So this has gone up by 2.16. And as we see, this and this, our carbon monoxide and our methanol, are in a 1-to-1 ratio. So if this has gone up by 2.16, this is going to go down by 2.16. So if you put that into your calculator, you get your answer of 17.9. So that is our moles of carbon monoxide at equilibrium. And here we see 1-to-2 ratio. So if this has gone down by 2.16, this is going to go down by double that, because this is a 2. We've got 1-to-2 ratio. So this is going to be minus 2.16, but times by 2, because this is 1-to-2. So therefore, if you put that into your calculator, you'll get your answer of 24.2 minus 2 times 2.16 minus that, and your answer will be 19.9, and that is your amount of hydrogen. So 17.9 moles and 19.9 moles. There you go. A different mixture of carbon monoxide and hydrogen was allowed to reach equilibrium at 600 Kelvin. At equilibrium, the mixture contained 2.76 moles of carbon monoxide, 4.51 moles of hydrogen, and 0.36 moles of methanol. Total pressure was 630 kilopascals. Calculate a value for the equilibrium constant Kp for this reaction at 600 Kelvin and state its units. So we're asked to calculate Kp, and it's given us a specific temperature because we know Kp changes with temperature. Any equilibrium constant changes with temperature. So let's use this equation again, because we're working with the same equation here. So we've got our carbon monoxide plus our 2 moles of hydrogen is going to make our methanol. And these are all gaseous. So I think also it's worth quickly writing out what the Kp expression for this would be, which is products over reactants, because that is going to get you a mark if you write out. So remember, it is circle brackets for partial pressure, not square brackets of concentration like in Kc or Kw. It's circle brackets because it's a gas and it's partial pressure. So our products, CH3OH, our methanol, over our partial pressure of hydrogen, and because there's a 2 there, it's 2 moles, put a big 2 there, and that is going to be multiplied by our partial pressure of carbon monoxide, and that is your Kp equation that we're going to be using. So the question has told us our equilibrium moles for this here. So our equilibrium moles for our carbon monoxide is 2.76. Our equilibrium moles of hydrogen is 4.51. And our equilibrium moles of methanol is 0.360. So now we need to think, how are we going to turn our moles that we've been given into partial pressures to put into the Kp equation to calculate our Kp? And so to do that, we need to turn them into partial pressures. So first of all, we need to calculate the total moles, because the only way to go to partial pressure is to go to from moles to mole fraction, and then if we multiply each mole fraction by the total pressure, we get the partial pressure of each gas, which we can put in the Kp equation. So get the total moles by adding each of these, and if you add all of the total moles up, 2.76 plus 4.51 plus 0.360, you will get your total moles to be 7.63. That is our total moles of all our gases. So if we divide each of these by 7.63, we will get our mole fraction for each one. But also you can kind of do this all in one go. So you don't have to just, so you could write out your mole fraction here and then write out the answer for each one of these. Or you could just do it all in one go, which is a lot quicker, and get your answer and multiply it by the total pressure. So you're going to multiply each one by the total pressure, which is given to you in the question. And the total pressure is 630. So if you multiply, so if you do this equation here, multiplied by the total pressure, you will get your partial pressure for each gas. So your partial pressure for carbon monoxide is 228. If you put that into your calculator, put this into your calculator, you'll get 372, and you'll get 29.7. So there we go, we have our partial pressures of each gas now, and we can put them into our Kp equation. So if we put 29.7 divided by our 372, but it's squared because it's our partial pressure of hydrogen squared, because we have 2 moles here, as we wrote out here, and that is also going to be multiplied by 228. So if you put that into your calculator, you will get a Kp value of 9.4 times 10 to the negative 7. I don't know if I've been 100% clear, but you don't need to write P's here. I'm just using this to demonstrate the fact that these are our partial pressures that we're using in our KP equation. You don't have to write that out. It's just so it's nice and clear. But yeah, so that gives us our KP, which is that there. And now we need to calculate the units. So to do that, I like to basically substitute the units for each partial pressure. Instead of numbers, I just like to put in the units, and you can essentially calculate it by doing that. So the units of partial pressure are kPa. So if we write out kPa, so this is essentially, these two here are the exact same, but instead of putting numbers in them, we've just written them out as the units instead to calculate the units. And we can see here, these two cancel out. So we're left with this here. And to bring this to the top, we basically just flip the unit, so that becomes a minus. So our units are going to be kPa to the minus 2. There you are. Table 4 shows some electrode half equations and their standard electrode potentials. So here we've got our electrochemical series and their E0 values in order. To reduce the oxidation state of nitrogen in NO3- and in NO. So here we've got 3 oxygens, so 3 times minus 2 is minus 6, and overall is 1 minus, so this must be plus 5, and that does make sense because nitrogen is in group 5. And then nitrogen in NO, this is minus 2, so this has to be plus 2, because overall it's neutral. State the weakest reducing agent in table 4. So a reducing agent is something, it causes something else to be reduced, or causes something else to gain electrons. Therefore, it in itself is being oxidized, because it's losing electrons, reducing something else. It's a reducing agent. So, if we look at table 4, if we remember, the most negative E0 value is the one that is most likely to be oxidized. It's the best at being oxidized. But we want the thing that is worse at being oxidized, the weakest reducing agent. Being oxidized in itself is reducing something else. So, if we look at the table, we can see that chloride ions here are the worst at being oxidized because it's got a positive E0. Because if you imagine the arrow going in that direction is when it's being oxidized, because it's going from chloride ions and making electrons and chlorine. So, therefore, it's being oxidized, and it's the worst at doing that because it's the most positive, as the most negative E0 is what's best at being oxidized. So this is the worst going in this direction. There we go. So it is Cl minus, don't forget the minus. Write the conventional representation of the cell that has an EMF of 0.43. So if we remember, EMF, or the E0 of the cell, should equal the E0 of the reduced minus the E0 of the oxidized cell. So if we put 0.43 here, we just need to look for the reduced and the oxidized cell. That gives us a value of 0.43 volts. And if you have a little scan of this table, through trial and error, you should be able to see that this minus this gives you your 0.43. So therefore, our cell consists of these two here. There you go. So we need to write the conventional representation of this, and you always do the oxidized one on the left, so the negative one, which is this one here, and the positive one on the right. So let's write our notation layout, and this here is the salt bridge. If you remember, you have 2 lines to represent a salt bridge, and let's start. So you have the reduced form. The way I like to do it is thinking reduced, oxidized, oxidized, reduced form. So the reduced form in this case is the copper solid here because it's gained electrons. So that is our reduced form, copper solid. And then we need the oxidized form of that. So that is going to be copper 2+ because it's lost 2 electrons. So that is copper 2+, and that is aqueous. Never forget the state symbols. You need the state symbols. And then here we need the oxidized form again, Fe3+. And I believe here there's been a mistake. This should be 2+, because this is actually left out of the mark scheme, this question. But I believe that should be 2+, because it's gained an electron. But yeah, so because it's the same state, aqueous, you kind of remove the line and you put a comma because they're the same state. So then you put the Fe2+, that's also aqueous, so you have the comma. And because they're both aqueous, you need a reaction surface for these two to react on. So you add another straight line and you add a platinum electrode. If you remember that from the standard hydrogen electrode, you need a surface for, you know, the gases and the hydrochloric acid to work on. You need a solid surface when, you know, they aren't in that phase. So yeah, you add platinum. Use the data from table 4 to identify an acid that will oxidize copper. Explain your choice of acid. Use these data to suggest a possible equation for the reaction and calculate the EMF of the cell that has the same overall reaction. So we need to identify an acid, that's one thing, and it's oxidizing copper. Therefore, it in itself is being reduced. So it's going to have a more positive E naught than copper. So if you go back to our data here, and we have a look at copper, this one here, is 0.34, and we need something that is going to be reduced. So this has to be oxidized. This is the negative one. Our copper is the negative one. So we need something that is more positive so it can be reduced, and it also has to be an acid. Can't be this because that's not an acid, and it can't be this because that's not an acid. If you look here, NO3 minus is the conjugate base for nitric acid, or HNO3. There's the H plus, there's the conjugate base. So that is going to be our one that is being reduced. So oxidized, reduced. So now we just need to put that into words. So our choice of acid, HNO3. You can't just write NO3 minus, you have to put HNO3 because it's asking for an acid. NO3 minus is a base, that's the conjugate base, so we need to add the acid. Then we need to explain this, and the way you explain this is by referring back up to the table. We see that our conjugate base of NO3 minus here, the one that is being reduced, is gaining the electrons. It has a more positive E naught than our copper 2 plus. So we just need to write that. NO3 minus has a more positive E naught value than copper 2 plus. You need to be specific. You can't say HNO3 has a more positive E naught because that's not the thing that's being reduced. Here we see NO3 minus is gaining electrons, so that's the thing that's being reduced. That's the thing that has the positive E naught because it's being reduced. And the same for this. Our copper solid here is the thing that's being oxidized. It's losing electrons, so that is the thing that has to have the more negative E naught. So we need to write copper. So yeah, there you go. And if now we need to write the equations. So in our electrochemical series, everything is always written in reduced format. We see they're all gaining electrons all throughout. They're all gaining electrons. So when writing an equation, we have one that's being reduced, one that's being oxidized. It's a redox reaction. So the one that's being oxidized, we need to write this arrow in the other direction, in the oxidized direction, because this is currently being reduced, but that's not what's happening in the reaction. It's being oxidized. So we need to make sure, first of all, to flip that arrow. And then secondly, we can see here that we need to combine our equations. We need to have an overall equation. But how can we combine equations that have different amounts of electrons? Electrons can't just like disappear. They need to be balanced. So yeah, to balance them, if we see we've got 3 here and 2 here, I'm thinking 6 electrons in total. So we can multiply everything in this equation here by 2. And then for this one, to get to 6, we can multiply everything in this equation by 3. And therefore, once we do that, the electrons will be balanced. There's no electrons just disappearing into space or too many electrons being made. We have the same amount, 6. So what you do is, to write out the overall equation, you flip the arrow going that way, and you balance the electrons, so you times everything by 2 and everything by 3. For the sake of time, I'm just going to write it out rather than go through it systematically, but in your exam you have to write out each equation systematically, multiply them by 2, multiply by 3, and then combine. So that will give you your overall equation of this here. So that's your overall equation, and it says calculate the EMF of the cell that has the same overall reaction. So to calculate the EMF of the cell, EMF is the E naught of the cell that's being reduced minus the E naught of the cell that's being oxidized. And the one that's being reduced here is 0.96, and the one that's being oxidized is 0.34. Or you could say plus 0.34, doesn't make a difference. And if you put that into your calculator, you'll get an overall EMF of 0.62 volts. So the EMF equals 0.62 volts. Alright, the dreaded back titration, a very long, comprehensive question with lots of writing. So there are many different ways that people like to do this, but I think the only method that really works is if you do a flow diagram, because, you know, we're given so much writing here, so much writing. So it's kind of just impossible to work with it. You can just like blindly calculate stuff. So the way I like to do it, and I think the way that you should do it, is by making a flow diagram. Then you don't need to use any of this, you know? You just work off your flow diagram and do it systematically. You identify something. So we're given Na2C2O4. You're given a mass and you write that next to it. So whatever thing you're given, you write the volume, the concentration, the mass, whatever it is, and you make a little flow diagram with arrows. So I'll demonstrate how to do this now. So this question is about compounds containing ethane diarrhea ions, and we're told that a white solid is a mixture of sodium ethane diarrhea and ethane diaric acid dihydrate, also an inert solid, but we don't care about that, it's inert, it doesn't react. And this is put in a volumetric flask containing 1.9 grams of this solid mixture in 250 centimeter cubed. So we've got our white solid. We are told this contains Na2C2O4, and we're also told this contains our H2C2O4 dot 2H2O. It's hydrated. So that is what we've got in the white solid, and as I said, you write out the mass next to it. So we've got 1.90 grams of this white solid. So you write mass equals 1.90 grams. We're also told a volume, 250 centimeter cubed, because it's in a volumetric flask. So you write out the volume, 250 centimeter cubed. So now we've got everything we need to know about this white solid here. We no longer need to refer to this up here. You know, this is done. We've got our little flow diagram of that, and it's much easier to digest this information. You know, it's a lot easier to look at. So now we're told we're doing 2 different titrations, and we're using this solution, you know, this volumetric flask with this mass, this white solid. We're doing 2 titrations with it. So what I'm going to do is I'm going to write out 2 little arrows. And this one will be titration 1, because we're doing 2 different titrations. The question tells us 2 different titrations. So we're told that we're using 25 centimeter cubed of our original solution. This is 250. We're now using 25. That is 10 times smaller. So just keep that in mind. So this is titration 1, and we're using 25 centimeter cubed of the original. So we've got 25 centimeter cubed of our original, and we're reacting that with an excess of sulfuric acid in a conical flask, and we're titrating that against potassium manganate. So we're adding potassium manganate. Write that down. And the question tells us that with this potassium manganate is 0.02 mole decimeter cubed. That's a concentration. So now we've got a concentration of our potassium manganate. So you're going to write that down. So we've got our concentration, and we've also been given a volume of how much potassium manganate. So that is 26.50 centimeter cubed. So that is titration 1 done. We no longer need to look at that now. We've written down everything that we need here. We're reacting 25 centimeter cubed of this with this much KMNO4. Now for titration 2, I also just want to quickly point out, you should write out that this equation here is what is going on in titration 1. So I'm going to write a little 1 there, and a little 1 there, just to refer, you know, that these are the same equation, because remember it's acidified, and we're reacting our MnO4 with our C2O4. That is from the white solid, that is the potassium manganate. Now, in titration 2, we're told that again, we're reacting 25 centimeter cubed of this. What are we reacting it with? Sodium hydroxide. So we write NaOH. Here is a volume, that's how much volume, and that is our concentration, all of sodium hydroxide. So our concentration of sodium hydroxide is 0.1. And our volume, we're told that we're adding phenolphthalein, and the indicator changed colour, that's the endpoint of 10.45 centimeter cubed of sodium hydroxide. So there we go. And that is our second equation. So I'm going to write a 2 there. I'll put it over here. So now we've written out everything we need to know for all of this. It's all down here now, and this is much easier to look at than before. And the question wants us to calculate the percentage by mass of sodium ethane diarrhea in the white solid. So that's this, our sodium ethane diarrhea. We want to find the percentage by mass of that in this whole white solid, the percentage of how much of this we have. So now we need to use all the data that we've got to find the moles of our Na2C2O4 in the white solid. And so we can start here at this equation here. We've got the concentration, we've got the volume. We can use that to find the moles. So if we go down here and we write that our moles of sodium hydroxide is going to be our concentration times our volume. That's how you find the moles, but this needs to be in decimeter cubed, so we're going to divide that by 1,000. So it's going to be 0.1 times 10.45 divided by 1,000. which is going to give us our moles, and that is, if you put that into your calculator, 1.045 times 10 to the negative 3. And if we see here, we've got our 2 moles of our hydroxide, and we can use that. If we divide this by 2, we can find the moles of our H2C2O4. So if we do, our moles of H2C2O4 will equal 1.045 times 10 to the negative 3. If we divide that by 2, we'll get our moles of H2C2O4. But bear in mind, this is in 25 centimeter cubed. Don't forget that, because this is what reaction is going on in this titration. It's reacting with this here, 25 centimeter cubed, not the 250. It's been diluted. So that's divided by 2 will give us our moles of H2C2O4, which is 5.225 times 10 to the negative 3. So now we want to find what this is in the original white solid in 250, because we want to find this here. We can find what our H2C2O4 is in 250. So we want to take our answer, which is our moles in 25, our moles of H2C2O4, and if we do that in 250 centimeter cubed, what's the difference between these two? 25 to 250 has been times by 10. So if we get our 5.225 times 10 to the negative 3, and we times it by 10, we get 5.225 times 10 to the negative 4. So now we have our moles of our H2C2O4 in our white solid right here. Titration 2 is done. This second equation here, we've done the working out for that. So now we need to move on to the first titration. So if we have a look at our first titration here, we see that we can calculate our moles of KMNO4. We've got the concentration and we've got the volume. So our moles of MnO4 minus is going to be the concentration times the volume. So 0.02 times 26.50, but we need that in decimeter cubed, so we're going to divide that by 1,000, or you can do times 10 to the negative 3, and that will give us our moles of MnO4 minus in this equation right here to be 5.3 times 10 to the negative 4. Now, we see here in our first equation that for 2 moles of this, we have 5 moles of C2O4 minus. They react in a 2 to 5 stoichiometric molar coefficient ratio. It's 2 to 5. So if we want to find the moles of C2O4 minus, what we can do is we can divide by 2 and times by 5. So if we want to find our moles of C2O4, we get our answer, 5.3 times 10 to the negative 4. And what we can do is, because we want to divide by 2 and times by 5, we can just multiply it by 5 over 2. It's the same thing. And that will get us our moles of C2O4 in 25 centimeter cubed in this reaction here, which, if you remember, 25 centimeter cubed of it. So in 25 centimeter cubed, we get our moles to be 1.325 times 10 to the negative 3. But we want to find in the white solid, and if you remember, we go from 25 to 250. So the only difference there is that it's been multiplied by 10. So if we get our answer of C2O4 minus in 250, we just have to get our 1.325 times 10 to the negative 3. If we multiply that by 10, you will get an answer of 1.325 times 10 to the negative 2. So now we've got our moles of C2O4 minus, which, might I point out, could be either of them, but we've definitely got our moles of H2C2O4, which we calculated here. So we can actually use all the data we've got now to calculate our moles of Na2C2O4. And if you look at what we've got, we've calculated the C242 minus moles, and that could be either of these, but we've also definitely calculated the moles of H2C2O4 here, and that is just this one here. So we can actually rule out this one by minusing our total C2O4 minus, which we calculated here, which is 1.325 0.25 times 10 to the negative 2, if we minus that by our moles of our H2C2O4, which we calculated before, to be 5.225 times 10 to the negative 4, so if you put that into your calculator, you'll get your moles of sodium C2O4, Na2C2O4, and that will give you your answer of 8.025 times 10 to the negative 3. So that is our moles of our Na2C2O4 in the white solid. But the question wants us to calculate the mass. So we need to find the mass of that. So we need to multiply it by its MR. Because if we want to find the mass, it's the MR times the mole. We've got the mole, we want to find the mass, we've got to multiply it by the MR. And the MR of Na2C2O4, if you use your periodic table, is 134. So that will give you your answer to be 1.075 grams. So now we found the grams of just our mass of Na2C2O4 in the white solid, but we want to find the percentage by mass. So what we do is we look back before, we saw the total mass is 1.90. So we do 1.075 divided by 1.90, and that will give you your percentage by mass if you times it by 100, because we need it as a percentage to be 56.6%. Ethane diioate ions react with aqueous ions in a ligand substitution reaction. Write an equation for this reaction suggests why the value of the enthalpy change for this reaction is close to 0. So we need to look at what we've got. We've got iron, and it's in the 3+ oxidation state, and it's aqueous. So that is going to be FeH2O6, 3+. Because it's aqueous, it's hexa-aqua coordinated. And we're adding ethane diioate ions. If you remember, ethane diioate ions are bidentate, meaning that, per ligand, this is just one ligand, we've got 2 oxygen atoms that are going to form a coordinate bond to our central transition metal ion, because there's lone pairs on both of these oxygens here. So we're only going to need 3 of those. They're not monodentate like water. Water only each ligand forms 1 coordinate bond to the central transition metal ion, meaning that you need 6 of them to form an octahedral complex. But because we got ethane diioate, and that's bidentate, we're only going to add 3. We're going to add half of the C2O4, 2 minus of our ethane diioate. And we're going to get complete ligand substitution here. So we're going to form FeC2O4, 3. And if each of these are 2 minus, and we've got 3 of them, and this is 3+, the overall charge of the complex that we're forming is going to be 3 minus, because 3 of these each have 2 minus. And yeah, the iron here, we're told, is in the 3+ oxidation state. And that is displacing all 6 water ligands. Because these are bidentate, they're fully surrounding, it's still octahedral, there's no change in coordination number. So yeah, that's it. And we need to suggest why the value of the enthalpy change for this reaction is close to 0. And if you remember, enthalpy change is just bonds broken by or minus bonds made, or the enthalpy of the products minus the enthalpy of the reactants. If we look at this in terms of bonds, there's no change in coordination number. We've still got 6 coordinate bonds, and they're all the same type of bond as well. They're all FeO. Here, with the water ligands, it's the oxygen donating a lone pair to the central transition metal ion Fe. And here we've got the oxygen on the C2O4, the lone pair, even though it is 2, it's still the same type of bond. So it's still 6 FeO bonds are broken, and 6 FeO bonds are made. So that is why your enthalpy change is the same. The bond's broken, the bond's made, identical. There's no change in coordination number, so there's no change in enthalpy. Draw the displayed formula of the iron complex produced in the reaction in 11.2 and indicate the value of the OFeO bond angle. State the type of isomerism shown by the iron complex. So the product here is our Fe, which is coordinated with our C2O4 bidentate ligands. So we need to draw that, and its displayed formula, we need to show all the bonds. So if it's still got a coordination number of 6, because if we've got 3 bidentate ligands, we've got 6 coordinate bonds. So it's still going to be octahedral. So draw out your standard octahedral complex. And we need to add our bidentate ligands in now, our ethane diioate ligands. So you need to draw all the bonds here. And people tend to forget this, and it's so annoying, but just don't remember, it's 3 minus charge, so you need to draw square brackets around it to show that the complex overall has a 3 minus charge. So if you kind of just need to remember this, but it's talking about the FeO bond angle. That's this bond here, or any of the ones in the octahedral kind of area, and you just need to remember that that is 90 degrees. And the type of isomerism, when you have bidentate ligands, you kind of just need to remember that you get that optical isomerism. If you remember, you get that non-superimposable mirror image of the complex when you have bidentate ligands. If you have monodentate ligands, you get cis or trans, but bidentate, you have this optical isomerism. So you just write optical there. Ethane diobate ions are poisonous because they react with iron ions in the body. Ethane diobate ions are present in foods such as broccoli and spinach. Suggests one reason why people who eat these foods do not suffer from poisoning. So there's one example that my chemistry teacher told me, and it kind of stuck with me. And vinegar is ethanoic acid or acetic acid. However, you can put vinegar on your chips. You can eat vinegar and you're not gonna get, you're not gonna die. Whereas in a lab, please don't do this. If you drink ethanoic acid, it's most likely going to be very corrosive and not good for you at all, and it's not going to be good. The only difference between the lab ethanoic acid and the vinegar is that the vinegar is obviously much lower in concentration. It's kind of common sense, but it's interesting to think about. So here, we can just say that the ethane dioic acid is in low concentration because it's not causing any effects if it's such low concentration, just like the vinegar example. So yeah, there you go, guys. I hope the walkthrough is helpful, and I try to answer it as best as I possibly can, but there is always the chance that there could be some mistakes in this. So if you do see any mistakes, feel free to let me know in the comments. If you have any questions, please let me know in the comments and I'll do my best to answer them.